Let's discuss the De Moivre's theorem. So here we have the following statement. If n belongs to the set of integers, then cosine theta plus I times sine theta raised to the power of n. This can be also represented as cosine of n theta plus I times sine n theta. So what we'll do, we'll try to prove this particular statement, and there will be three cases. The case number one, let's divide it into the cases. So case number one, we'll consider for n equals to 0. Then in case number two, we'll consider n to be positive integer. And in case number three, we're going to consider the case of n as negative integers. So let's begin with the first one, case number one. So in case number one, we are going to begin by considering when our n value, that is 0. So in this case, cosine of theta plus I times, I is iota, the imaginary number, times sine theta whole raised to the power of n. So our n value is equals to 0. Right. So this value, so that's going to be equals to 1. Now 1 means this is a purely real number. There is no imaginary part here. So since there is no imaginary part, so our 1 can be also represented as 1 plus iota times 0. That means the imaginary part is 0. Now we know that the 1 value, that's also cosine of 0 radians, that gives us the value 1 plus I times 0 can be also represented as sine of 0. So we have cosine of 0 plus I times sine of 0. So cosine of 0 we have, so 0 can be also represented as 0 multiplied to theta plus iota times sine 0 times theta. So that means we have successfully shown that whenever n equals to 0, then the De Moivre's theorem states that cosine theta plus I times sine theta raised to the power of 0, this will be equals to cosine of 0 theta plus I times sine of 0 theta. Now what we'll do, we'll go to the next part of the proof. We'll try to prove this for a positive integer value of n. So let's do that as well. So case number 2. So in case number 2, we are going to consider when n belongs to the set of positive integers. Right. So let's do that. The first what we'll begin, we'll use the theorem, we'll use the method of induction to prove the following theorem, the De Moivre's theorem. So let's say this theorem is true for n equals to 1. Now that's because this is true because if we consider our original equation, which is cosine theta plus iota times sine theta raised to the power of 1, so that will be also represented as cosine of theta plus I times sine theta. Now instead of theta, what we can do, we can rewrite it as 1 multiplied to theta plus I times sine multiply a sine of 1 times theta. So we can show that the De Moivre's theorem holds true for n equals to 1 value. So we'll assume that the theorem is also true for n equals to m value, where m is another positive integer. Then in that case, we can say that cosine of theta plus I times sine theta raised to the power of n. So this must be equals to cosine of m theta plus I times sine of m theta. Our next task will be to prove that the theorem is also true for n equals to m plus 1. So that means cosine of theta plus iota times sine theta raised to the power of m plus 1. Then we can rewrite this as cosine of theta plus I times sine theta whole raised to the power of m multiplied to cosine of theta plus iota times sine theta raised to the power of 1. So here we use the law of indices. Now this particular expression can be replaced with cosine of m theta plus iota times sine m theta, because we have already shown that it's true for n equals to m value. So this will get multiplied to cosine of theta plus iota times sine theta. Now we'll multiply them. So this will give us cosine of m theta multiplied to cosine of theta plus iota squared sine m theta times sine theta plus iota times, so we're going to take iota as the common factor, so this will give us cosine of m theta times sine theta plus sine m theta times cosine of theta. Right. Now iota squared, that value is equals to -1. So this iota squared, this value is -1, so we can replace it with -1, and this is going to give us cosine of m theta times cosine of theta minus sine of m theta times sine theta plus iota times cosine of m theta times sine theta plus sine m theta times cosine theta. Now cosine of m theta times cosine of theta minus sine m theta times sine theta, this is the expansion of cosine of m theta plus theta plus iota times, and this particular expression is the expansion of sine m theta plus theta, which means we have cosine of m plus 1 times theta plus iota times sine of m plus 1 of theta. Right. So we have successfully shown that the Moivre's theorem is true for n equals to a positive integer. So that means whenever we have cosine theta plus I times sine theta raised to the power of m plus 1, so we are getting cosine of m plus 1 theta plus I times sine of m plus 1 theta. So the general statement that cosine of theta plus iota times sine theta raised to the power of n, so this will be equals to cosine of n theta plus iota times sine n theta, and this is going to be true for all values of n belonging to the set of positive integers. Now let's go to the third case. In our third case, case number 3. So in our third case, we are going to consider the case that n is a negative integer. N is a negative integer. That means simply n belongs to the set of z minus. It's the set of negative integers. Fine. So let's do that. So for this, what we'll do, we'll replace simply n with negative n. We'll have cosine of theta plus iota times sine theta, whole raised to the power of n. So this will be equals to cosine of theta plus iota times sine theta whole raised to the power. So instead of n, we will replace it with negative n. Now this can be also expressed as 1 over cosine of theta plus iota times sine theta whole raised to the power of m. Now we have already shown that now here m becomes a positive number. So here we can we have already shown in the previous case that this will be equals to cosine of m theta plus iota times sine m theta. Now what we have to do, we have to convert it into our standard form. To convert it into a standard form, what we'll do, we'll multiply both the numerator and the denominator with the complex conjugate of this denominator, which is cosine of m theta minus iota times sine m theta, and we'll also have to multiply to the numerator as well. So we'll have cosine of m theta minus iota times sine m theta in the numerator. So what we'll do, we'll simplify this. This is going to give us, in the numerator, we're going to have cosine of m theta minus iota times sine m theta whole divided by, so here this is an identity, a plus b times a minus b. So we'll have cosine squared m theta plus sine squared m theta. So here we have used the fact that I squared is -1. So the denominator term goes to 1 because that's a standard identity, and this leaves us with the value cosine of m theta minus iota times sine m theta. Now this can be also expressed as cosine of negative m theta, because we know that cosine of, let's write it down here, cosine of negative theta, this value is simply positive cosine theta, and cosine of and sine of negative theta, that's equals to negative sine theta. So in a case we have negative sine m theta, this can be also expressed as plus iota times sine of negative m theta. So therefore, we started out with the fact that we have cosine of theta plus iota times sine theta raised to the power of negative m. So this is going to giving us the value cosine of negative m times theta plus iota times sine negative m times theta. So that means De Moivre's theorem, cosine of theta plus iota times sine theta raised to the power of n, where n is a negative integer, this will be also equals to cosine of n theta plus iota times sine n theta, and here n belongs to the set of negative integers. Let's try to apply the De Moivre's theorem with the help of an example. So here we have cosine of theta plus iota times sine theta whole raised to the power of 5. This is the numerator part. We'll leave it the way it is, and the denominator, this is our numerator, and the denominator is cosine of theta minus iota times sine theta raised to the power of 6. Right, this is the denominator. But what we'll do, we'll try to rewrite the denominator. We can also express the denominator as cosine of, we can write cosine of theta as cosine of negative theta. It is still going to be positive, but we have negative sine theta for the imaginary part, which can be expressed as positive iota times sine negative theta, and this entire thing is raised to the power of 6. Now what we can do, we can use a De Moivre's theorem to rewrite this expression as cosine of theta plus iota times sine theta whole raised to the power of negative 1, and this also entire thing is raised to the power of positive 6. So this will be equals to cosine of theta plus iota times sine theta raised to the power of negative 6. Negative 1 times 6 will be negative 6. Now that means our expression cosine of theta plus iota times sine theta whole raised to the power of 5 divided by cosine of theta minus iota times sine theta raised to the power of 6. This can be also expressed as cosine of theta plus iota times sine theta raised to the power of 5. Now the denominator can be expressed as cosine of theta plus iota times sine theta raised to the power of negative 6. So the numerator and the denominator, so the base is exactly the same, so we can take it to the numerator and combine them to get cosine of theta plus iota times sine theta raised to the power of 5 plus 6, which is going to be, this is going to be equals to 11. So that means we have cosine of theta plus iota times sine theta whole raised to the power of 11, and using again the De Moivre's theorem, we're going to get cosine of 11 theta plus iota times sine of 11 theta. So let's try to simplify the given expression. We have cosine theta of I times sine theta raised to the power of 4, and we have cosine of theta minus iota times sine theta whole square. So let's begin. So our first expression, which is cosine of theta plus iota times sine theta, let it remain the way it is. It's raised to the power of 4. Now cosine of theta minus iota times sine theta, this can be also expressed as cosine of negative theta plus iota times sine of negative theta whole raised to the power of 2. So this will become cosine of theta plus iota times sine theta whole raised to the power of 4, and this expression can now become cosine of positive theta plus iota times sine of positive theta. Since it's multiplied with negative 1 here, so we can raise the negative 1 and multiply it to 2 to give us negative 2. So that means we now have cosine of theta plus iota times sine theta whole raised to the power of 4 minus 2. That will be equals to cosine of theta plus iota times sine theta whole squared. And finally, again applying the De Moivre's theorem, this is going to give us cosine of 2 theta plus iota times sine 2 theta. So this is the simplified form of this particular expression. So let's try out number 3. So here what we can do, we can apply De Moivre's theorem to each of the expression. Now in the numerator we have cosine of 3 theta plus iota times sine 3 theta. So that means this can be expressed as cosine of theta plus iota times sine theta raised to the power of 3 whole raised to the power of 4. For the second expression, we have cosine of 4 theta minus iota times sine of 4 theta. We can express this as cosine of theta plus iota times sine theta raised to the power of negative 4 whole raised to the power of positive 5. So we'll have divided by cosine of theta plus iota times sine theta raised to the power of 4 whole raised to the power of 3. And for the second expression, we have cosine of theta plus iota times sine theta. This is going to be raised to the power of 5 whole raised to the power of negative 4, which will give us cosine of theta plus iota times sine theta raised to the power of, so 3 times 4 will be 12, multiplied to cosine of theta plus iota times sine theta raised to the power of negative 20 whole divided by cosine of theta plus iota times sine theta raised to the power of 4 times 3 will be 12 times cosine of theta plus iota times sine theta whole raised to the power of 5 raised to the power of 5 multiplied to negative 4 will be negative 20. So here all the expressions will get factored out and this will leave us with value 1. So that means the value of the given expression is actually simply 1. So let's try to simplify this expression with the help of De Moivre's theorem. We'll begin by rewriting the expression in the numerator as cosine. So here we have cosine of 5 theta minus iota times sine 5 theta. So that will be cosine of theta plus iota times sine theta raised to the power of negative 5 whole raised to the power of 2 over 5. Multiply to the second expression. So we have cosine of 2 over 7 theta plus iota times 2 over 7 theta. This will become cosine of theta plus iota times sine theta raised to the power of 2 over 7 whole raised to the power of 7. The entire expression is divided by, so here we have cosine of 4 theta plus I times sine of 4 theta. So we have cosine of theta plus iota times sine theta raised to the power of 4 whole raised to the power of 1 over 4 times. So here we have cosine of theta plus iota times sine theta whole raised to the power of 2/3 and entire thing is raised to the power of 3. So that means we now have cosine of theta plus iota times sine theta raised to the power of, so here the exponents will get multiplied with negative 5 multiplied to 2 over 5. So that's simply negative 2. This will be multiplied to cosine theta plus iota times sine theta whole raised to the power of, so 2 over 7 times 7, that will be simply 2. Whole thing divided by cosine of theta plus iota times sine theta whole raised to the power of, so 4 times 1 over 4 will be 1, multiplied to cosine of theta plus iota times sine theta raised to the power of, so 2/3 multiplied to 3 will be simply 2. So now we will combine the expressions. So in the numerator, so we have negative 2 and positive 2 here. So this will simply goes to, so let's write it down here, cosine of theta plus I times sine theta whole raised to the power of negative 2 plus 2. And in the denominator, we have cosine of theta plus iota times sine theta raised to the power of 1 plus 2, which is going to give us cosine of theta plus iota times sine theta raised to the power of 0, and 2 plus 1, this is going to be equals to 3, so we'll take it to the numerator and multiply it to the numerator to give cosine of theta plus iota times sine theta raised to the power of negative 3. So this expression goes to 1, so that means we are now finally left with cosine of negative 3 theta plus iota times sine of negative 3 theta. Or simply put, we have cosine of, since cosine of negative theta is positive cosine of theta, so we'll have positive cosine of 3 theta minus iota times sine 3 theta. So this is going to be the simplified expression for this given expression.